The chemistry department owns two Fourier transform IR spectrometers, often just called FTIR. The first is a Perkin-Elmer Spectrum 1 FTIR, which we refer to as Spec 1. And the other is a Perkin-Elmer Spectrum 2 FTIR, which we refer to as Spec 2. Each instrument is capable of obtaining information about infrared radiation at all frequencies simultaneously as the radiation is passed through the sample. This diagram shows the basics of how we obtain infrared spectra using an FTIR spectrometer. A beam of infrared radiation is directed into a part of the spectrometer called the interferometer. The interferometer consists of a beam splitter and a pair of mirrors at right angles to each other. This produces what's called an interferogram, which stores information about the IR radiation at all frequencies simultaneously. When the radiation arrives at the sample, some frequencies are absorbed by the sample and some are allowed to pass or be transmitted through the sample. When the transmitted radiation arrives at the detector, information about that radiation is decoded using a mathematical technique called a Fourier transformation. This provides information about the intensity of transmitted infrared radiation at each frequency separately. The computer software then produces a graph of percentage transmission against frequency or wave number. And this graph, called the IR spectrum of the sample,
we are going to learn the types of molecular vibrations in infrared spectroscopy with the help of animation. We have two main different types of vibration. Out of that, one is stretching vibration and the other one is bending vibration. In stretching vibration, we have two types, that is symmetrical as well as anti-symmetrical. In symmetrical vibration, you can see here in animation that both the atoms are going away from the central atom and simultaneously they are going towards the central atom. It means that there is change in the bond length. Here, this is the second stretching vibration, that is anti-symmetrical. Here also you can see the little bit change. One atom is going away from the central atom and the other one is going towards the central atom, and the vice versa. When the other is going away from the central atom, at that time the first one will go towards the central atom. It means that again there is change in the bond length in this antisymmetrical vibrations. We have second major type, that is bending vibration. These bending vibrations are again four types. The first one is scissoring. Scissoring vibration is in a plane vibration. Here both the atoms are coming towards each other and simultaneously they are going away from each other, but both the atoms remains in the same plane. So that's why scissoring vibration is in a plane vibration. Now we have rocking vibration. Again, rocking vibration is again in a plane vibration. Here you can see both the atoms are vibrating in the same plane. You can see it is in a clockwise direction as well as in an anti-clockwise direction. But the important part is both these vibrations are in a plane vibrations. But if you compare these two with wagging, you can see both the atoms are coming towards us and simultaneously both the atoms are going far from us. Means they are not in a one plane. So that's why wagging vibration is out of plane vibration. So here you can see clear cut that both the atoms simultaneously are coming towards us. It means that there is disturbance of the plane, so atoms are not remaining in the same plane. Similarly, twisting vibration is again the out of plane vibration. Here one atom is coming towards us and the other atom is going far from us. That's why again twisting vibration is out of plane vibration. And due to all these six vibrations, the molecule get vibrate and the molecule get absorbed in infrared spectroscopy.
Infrared radiation can cause bonds of molecules to vibrate by stretching and bending them. The frequency of the infrared radiation which causes the bond to vibrate can be characteristic of the bond. For example, consider the carbonyl group C double bond O. When infrared radiation in the range 1640 to 1750 centimeters to the -1 is directed towards a molecule containing C double bond O, this radiation is absorbed by the bond, causing it to stretch. How the instrument works. A thin layer of sample is placed between two sodium chloride discs. Sodium chloride is transparent to infrared radiation. A scan is made by running different frequencies between 450 to 4000 centimeters to the -1. The different types of bond within a chemical absorb infrared radiation at different frequencies, since bond strengths vary for the different types of bond. When molecules absorb infrared radiation, not as much radiation passes through the sample, and so the response from the detector is low. In regions where the molecule does not absorb strongly, the response from the detector is high, as the radiation passes through the sample largely unaffected. A spectrum is then produced, where the wave number in centimeters to the -1 is plotted along the x-axis, and the detector response, or percentage transmittance, is plotted along the y-axis. The peaks in the spectrum show where bonds within the molecule have absorbed infrared radiation. In AS chemistry, you only need to be able to recognize a few key peaks.
Identificar uma amostra através de um espectro no infravermelho é semelhante a um jogo de quebra-cabeça. Vejamos através de um exemplo como funciona esse jogo. As peças de nosso quebra-cabeça são os modos de vibração das moléculas. As moléculas não vibram de modo aleatório, elas vibram apenas em determinados números de onda. Nosso desafio é identificar os modos de vibração associados a cada pico. Inspecionando o gráfico, notamos a presença de 3 picos largos, em 3.347, em 1.430 e em 662. Esses picos estão sempre presentes em moléculas com radical OH. O pico com número de onda igual a 3.347 está relacionado com o modo de vibração de estiramento OH. O pico com número de onda igual a 1.430 está relacionado com o modo de vibração de balanço OH. O pico com número de onda igual a 662 está relacionado com o modo de vibração de abanar. Continuando a inspeção do gráfico, notamos a presença de 3 picos estreitos e agudos. Em 2.945, em 2.833 e em 1.460. Esses picos estão sempre presentes em moléculas com radical CH3. O pico com número de onda igual a 2.945 está relacionado com o modo de vibração de estiramento antissimétrico CH3. O pico com número de onda igual a 2.833 está relacionado com o modo de vibração de estiramento simétrico CH3. O pico com número de onda igual a 1.460 está relacionado com o modo de vibração de balanço antissimétrico CH3. Notamos ainda a presença de um pico com número de onda igual a 1030. Este pico é sempre encontrado em moléculas que têm um átomo de carbono ligado a um átomo de oxigênio e está relacionado com o modo de vibração de estiramento carbono-oxigênio. Podemos concluir que a molécula tem 2 radicais, CH3 e OH, e que estes radicais estão ligados. Este espectro é, portanto, de uma amostra de metanol. A amostra está identificada. O jogo acabou. O espectro de uma amostra é semelhante à nossa impressão digital. Assim como não existem duas pessoas com impressões digitais idênticas, também não existem duas moléculas diferentes com espectros idênticos. Assim como nós, uma molécula também tem identidade única no universo.